Okay, good morning everyone. Okay, I think last time we discussed up until the implicit solution, right? So I think, let me check first. Okay, I think I forgot to mention just a few notes that is, I believe, uh, in learning the engineering of math or specifically the differential equations. Let me give you like a reasoning, like how to get into the differential equations. Okay, so I think I need to. Okay, so first we think that every phenomenon or everything that can be modeled, right? Like the rate of change or anything that has changes, we can have that as in our differential equation. So first is a model. So model of the rate of the rate of change, which means that sometimes we are seeing the y prime, for example, plus 2 equal e to the x, for example. That is one way to describe the differential equations. And then second, we need to relate derivative in equation. Yeah, I think this is what I meant. Remember that derivative, this will relate to changes, and we are not focused necessarily on numbers as our solutions. Focus on equation as solution. Okay, and 3 for the solutions, usually more than 1. Okay. That satisfy differential equations. Can I write number 4 up here so that we're still in the same page? Let me give you 4 here. Okay, and number 4, usually we have what we call the initial condition. To get what we call a particular solution. So if you see the word particular solution, you need to have some conditions to get it. And then regarding the order, the highest derivative in differential equation. So the nth order, they will have nth parameter family of solutions. So we could say if order increasing, then the constants also increasing. And the last one, 6. In ordinary differential equations, all will be based on independent variable x. Okay. I hope you can read it. This is just to show you how we could track the points in differential equation. So first, we start with the model of the rate of change that we can derive from any phenomenon. For example, radioactive decay, or change in temperature, or change in maybe economy. Also, we can also observe. So we have the models, and from the models, we need to relate the derivative in the equations. For example, we can relate like this first order, dy dx over y prime plus 2 equals some other equation of x. That is we call the differential equations, and the derivative will relate to the change. Okay. And what we are doing in our differential equations is we not focus on finding numbers as solution, as usually you find in calculus or in basic of mathematics. We usually find solutions as numbers, like x equals something, etc. Right? But here, what we are focused is the solution will be the equation itself, because what we are asking is the differentials. We need to know what is y. So we are going to approach those solutions from these differentials. And of course, if you remember, in calculus, we have differentials, we have integrals. If you want to make the differentials back to the original equations, we need to integrate them, right? And when we integrate, we plus the constant. It means that when we increase the order from the first order, second order, and maybe 3, 4, 5, it means that every time we integrate, we are getting plus constant more and more. That means all the order, if we get higher, then the constant also will get higher. Okay? And then, what else? Oh yeah, the solutions, it can be more than one. As I mentioned, we can have many different solutions, and it's okay. But later, we need to categorize what kind of solution do we want. Okay? Like last time, we have the trivial solutions that it's meaningless. It's a solution, but it's meaningless. For what? Then what we want to find later on is, one of them is we call the particular solution. The particular solution which we get from the initial condition. So because we have so many solutions, we need to approach one of them or several of them within some restrictions, or we need to limit the conditions. Okay? Which interval do we want? If you remember what we have in the 1 over x. 1 over x can be greater equal 0, greater 0 or less than 0. But which interval do we want? Because they are going in different directions. Okay, so that is the just some descriptions on what we are going to learn, at least for the differential equations, for the ODE we call the ordinary differential equations. Okay, we are going to continue. Okay, you can write for a while. Okay. I hope you get my idea for this part. Okay, let me continue for a while. So since we are talking before about the families of solution, so let me just give you some notes here that the end order, for example, of the differential equations. Let's say f. We usually write x, y prime, and then dot 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 y with order n, and we seek n parameter of solutions. Let's say the solutions is g, and g is also x, y, and perhaps the constant 1, constant 2, dot dot dot. Let me take all of this right here, and this will be equal to 0. And the implications is single DE can have infinite number of solutions. Okay, and then one definitions that can help to understand a solution that is free of arbitrary constant or parameter. We call the particular solution. For example, we have the graph here that's showing you some infinite solutions. This is the from DE xy prime minus y equal x squared sine x. And we propose the solution as and if you see from the left side, we see that depends on the constant, the constant that is on the solutions. We could have many ways to describe the solutions, and we call this kind of solution as a family of solutions. So we call that this is an explicit solution of the DE and based on the constant, the C, we could see some differences. Okay. Okay, again, I'll give you another example. Right here. Suppose we have DE xy prime minus 4y equals 0, and then we need to verify the equation y equals cx with power of 4. Okay. Now, since this is, I think, pretty simple, then the possibility for C, we can make it positive or negative, right? The only way to see this solution. So we could have Y can be a negative or can be positive, okay? In general, right? And this will be when x is less than 0, or this is x greater or equal 0, okay? We can have a piecewise defined solution as well, okay? So it depends on the interval. And the next question will be which interval? Okay? And to know which interval, we need to know the initial condition. Later we have some sections to get into the initial condition. So we are going step by step. So this is just definitions, classifications, category. Okay. Okay. So we could say, or if you want to write first, but let me just take to another page. I will write the same thing here. Already here. Okay. So this is the piecewise defined solution. So this is from y equals cx4, which is on the first graph. Okay, let me put here. And this is the sorry, this is supposed to be the solutions, not the DE. This is DE, family of solution. And then we make the solutions. So we take the particular solution by choosing c equal -1 for x less 0 and c equal 1 for x greater equal 0. So this is the particular solution. As I mentioned last time, also we have the trivial solution, or we call also a singular solution here. This is a solution that is not a member of family of solutions. So this is like an extra solution. So our trivial solution y equals 0 can be also a singular solution, because the y equals 0 is not a member from the family of solutions. So we could write that trivial solution y equals 0 can be a singular solution. Okay, one more sections to finish off this first part. Here. This is what we call the systems of differential equations. So what will we discuss on the systems is the equation can be more than one. Okay. So the differential equation can be more than one. So suppose that let me write two or more equations involving the derivatives of two or more unknown functions of single independent variable. So we are mainly focused on a single independent variable. So we are not yet going to talk about the partial if we have two independent variable. For ODE. And as example, we could think like in a parametric equation. If you remember calculus 2, we deal with parametric equations. We have x, y, and additional t, right? So we can also make that as our systems, okay? Because we have a system of x and y, and those x and y depends on the t. Okay, so we could write, for example, dx dt as a function for t and then x, y, and we can mention t here as our independent, and both x, y are dependent. Or dy dt, let's say g, we have t, x, y, and again this is independent, and this will be dependent. Now the solution that can be proposed, I think I will write here, I will put resize a little bit. So the solutions that can be over is x will be, let's say we have some functions psi 1 of t, and y is another psi 2 of t. And they need to be defined on the interval, okay? Define on interval satisfy DE. Okay. Now, of course, if we are getting some interval and then our solutions also having some interval, and we have also infinite number of solutions, right? So we don't want to have those many, and we want to like restrict some of them. And that is what we are going to do in the next section. We are going to limit how many solutions we are going to have, and those are usually we are set some initial conditions. We set some points that we want to observe. Okay. Yeah, it's supposed to be here, but let me just skip this. Okay, so initial value problems, or sometimes we call the IVB. Okay. So in differential equation, what we are going to solve, of course, it's the differentials And we can solve this, okay, by initial conditions. So solve with the subject to some points. So we could take some input for some x to define the value or y. We could have one or more, depends on the order. Okay, the more order you have, it means that the more initial condition you need to restrict. Okay? So this is for the first order, and for second order we need to limit the or we need to restrict the first derivative. And so on and so forth. Okay. So if we focus only if we are focusing only on first and second order, so if we have the first order, it means that this is the function, and we need to have one conditions that is okay. So solve this, and then this is initial condition. Okay. And this is true. If you remember the when you integrate something, you have the plus constant, right? At least. But if you integrate twice, you have two constants. So you need to have two. So if we increase the order, then we need to have two initial conditions. Okay? You get that logic? So if we are having the second order, sorry. X, y, y prime, right? And then we need to have, first is y, x0, y0, and then we need to also to restrict the first order or the first derivative. So you can imagine if you have the third order, the fourth order, then the initial condition will also increase. Okay? Why you need this? Because that is how you can restrict your solution. If not, then you will have the constant still there, right? And I think for the first order and second order, we can describe in a curve. I think still can be easily understandable for this first and second order. So if we see this part here, for the first order, okay, we are finding the solutions of the dE on the interval, the I interval that has the x0. So we pinpoint our solutions on this point, and this blue curve is the one we want. Okay, we may have infinite number, right? For example, the red one here we can have, okay, but we need to find the number that is restricted, which is our initial condition, which is this condition. For the second order, however, aside from just one point here, remember what will this describe? Y prime. It's the slope. That's why we have the slope here. That we need to make sure that this slope here is equal to y1 in geometric terms. And if you increase the order, then it means that you will have another geometric terms, and if you are increasing more and more, it will be very complicated to describe in the picture. And I think we need to use some graphing calculators to describe. But I think for the first order and the second order at least, we can describe using, so for the first order, we can just define as the point on the interval that we want. And the second order, aside from the point, we need to make sure that its tangent, the tangent line, the slope or the gradient need to be equal to y1. Okay? Because this is describing our tangent, right? Let me write here, just to make sure we are clear on this. Because this is describing the slope of the tangent line with gradient is m. Okay, I think we can go through. The example for this IVP is just to verify some solutions to some differential equation. I think we can do that later on when we have also the techniques to solve. Okay. Okay, the next part is the existence and uniqueness. Okay, so let me start with, let me just put the graph for a while. So we need to ask ourselves, okay, usually one or two fundamental questions for these IVP. So questions in an IVP problems, or IVP. We need to find whether the solution exists and if it exists, is it unique? What will these terms means? Let's say, so we are going to describe what is the existence and what is the uniqueness. So existence we start by asking the question again. So does dE, let's say dy dx equal fxy possess, or maybe it's too difficult to write, maybe has or have solutions? And then the following questions: do any of the solution passing x0, y0 as we mentioned in the IVP? Let me write, sorry, this is existence. And uniqueness is when can we certain that there is precisely one solution curve pass through okay. Okay, this picture, I think I need to put down first at the very, very bottom. Okay, so for dE f dy dx and initial value y of a equal b. Of course, this is at this point AB. So if f continues around point AB, let me write with different color. An open interval around x equal a, then at least one solution exists on an open interval around that x equal a, around x equal a. Now if fxy not continuous, then a solution is not this is guaranteed, so it's not certain, okay, at that point. And notes that x equal a is not the end of the point or the interval. This is some descriptions on the existence. We're going to have some example later on, okay, but I think because I don't have time now, we are continuing this part next week. But before that,